Okay, so there's two topics for today. The first one is free radical halogenation, and then we're going to move into dienes. So for free radical halogenation, what we're going to do is we're going to replace or substitute a halogen for a hydrogen in an alkane. So we should probably take a step back and just say, okay, for an alkane, we started with alkanes and we went into Newman projections and naming and all of that, but we really didn't do any reactions of alkanes because there's really only two. Just like with ethers yesterday, you can take an alkane, react it with oxygen and a flame, and you can combust it to CO2 and water. And synthetically, that's not helpful because I'm not making a bigger molecule, but unless you're driving like a Tesla, you use this reaction to get here this morning, or unless you walked. Okay. And even if you did use an electric car, somebody burned an alkane or an aromatic compound to make the electricity that you charged it with. So combustion is important, but it's not necessarily useful because I'm not making a bigger molecule. The other thing that we can do with an alkane then is we can replace the hydrogen with a halogen. And this turns out to be an important reaction because if we're going to start with an alkane and I want to make a bigger molecule out of it, or I want to add a functional group, the first step is to replace the hydrogen with the halogen. Because then what can I do with that halogen? Well, you can think of all the reactions that we've done. I could do SN2 or SN1, right? I could replace that Br with an OH. I could I could make a Grignard out of this alkyl halide and add a carbonyl to it. I could do E2 and make an alkene out of it. So any of those reactions can only be done if I replace a hydrogen with a halogen and an alkane. So if I'm going to use an alkane as my starting material, I need to be able to do this free radical halogenation. Okay? And the simple fact is we have two sources of organic compounds. We got crude oil and we have coal. Crude oil, alkanes, alkenes, and alkynes, mostly alkanes. Very few aromatics in crude oil. Coal, mostly aromatic. So those are our two sources of organic molecules. And so we have to be able to do something with alkanes. This is what we're going to do, is free radical halogenation. So free radical halogenation is a substitution. And how am I going to do it? I'm going to react the halogen, Br2, Cl2, we're going to spend most of our time on, and we can use either light or heat as what we'll call the initiator. Okay, so this is what we're going to do. If you say, okay, if I'm going to do this reaction with Br2, where's the other Br go? In addition to substitution, I make HBr. So this is the reaction that we're going to need to do. And we're going to start with something simple like methane. But we're going to work our way up to more complicated molecules because the question is, where does the Br go? Can I control where which carbon the Br adds to? And the answer is going to be yes, but we need to work our way to that. So this is typically a first semester topic in most books, except Top Hat. They made it a second semester topic. So if you've been through the first semester and you've already talked about this, hopefully it's a review. But if not, we're going to take it as if it isn't a review. We're going to take it from scratch. Okay. So the first thing is mechanism. So let's say I react methane, where I'm going to replace this hydrogen. I'm going to react this with bromine. I'm going to make my methyl bromide and my HBr. That's the overall reaction I'm going to do. I'm going to do this reaction in 6 steps. Okay. The first step is called initiation. And so in the initiation step, what happens is that my bromine molecule, and not all the bromine molecules, we really only need 1 or 2, are going to react with either the light or the heat, and they're going to break apart so that each bromine gets an unpaired electron. So we're using half arrows or fish hooks to indicate the breaking of that bond and each atom getting 1 electron, which is the way it should be because they both have the same electronegativity. So each one should get an electron, which means I'm going to end up forming 2 bromine. And if I put in the 3 lone pairs around the bromine, those are just bromine atoms. I mean, we'll sometimes call them bromine radicals. The radical term just means something has an unpaired electron. But this is really 2 bromine atoms. Okay, and this is an initiation process. So this starts the reaction. Then we have what's called propagation. So in the propagation step, what's going to happen is you're going to use that bromine atom to basically make the product. But in that process, you're going to release another bromine atom. Now, let me go back to the initiation step for a minute. What's the transition state of that reaction going to look like? Of the initiation step? I'm averaging bonds and charges. And in this case, there's going to be no charge. So what bond am I breaking? The Br-Br bond. So what should go between the 2 Brs? A dotted line. So in the transition state, I've got a partial bromine-bromine bond because I'm breaking it. Okay. So now my Br dot is going to react with one of the hydrogens of the methane. And this process is what's called abstraction. So the technical term is the bromine is going to abstract a hydrogen from the methane. And so what's going to happen is I'm going to break this carbon-hydrogen bond. The carbon's going to get its electron. The hydrogen is going to use its electron to pair up with the Br dot. So the arrows will go like this. And what I try and do is I try and write the molecule with the hydrogen, the carbon-hydrogen bond pointing at the bromine to make the arrows a little bit easier to work with. Okay. I'm going to go through a transition state. And on the other side, I'm going to form the hydrogen-bromine bond and a CH3 dot. So the H is going to become an H dot, pair up with the Br dot to form HBr. And then the CH3 is going to get its unpaired electron to form the radical. And so what's that transition state going to look like? We're going to have a Br, the H, and the CH3. What bond am I making? The Br H dot. What bond am I breaking? The carbon hydrogen. So we've got dotted lines in between the Br, the H, and the C, showing the forming and the breaking of those bonds. So normally when we write transition state, we put in the bonds and the charges. Do I have any charges so far? No. So there's no charges to put in the transition states, because this is all neutral radicals. Okay. So there's step one. So I just made a methyl radical. First thing, is a methyl radical stable? We should probably go back and review our radicals. So when you have a radical that is an sp2 hybridized carbon, we last talked about radicals at the end of Organic 1 when we talked about free radical, or when we talked about HBr peroxide to do anti-Markovnikov addition. That was our first radical. So it's sp2 hybridized and the carbon has an unpaired electron in the p orbital. It has 7 electrons. It's not happy, but it's happier than a carbon that had 6 electrons, which would be a methyl carbocation, which we're not allowed to draw the structure of in this class. So the CH3 plus would be very unstable, but a CH3 dot is still unstable, but it's more stable than a carbocation. So we can write its structure. Okay. And the more alkyl groups you attach to the radical center, remember that the carbon becomes slightly negative by taking electron density away from each hydrogen. So every time you attach a carbon to the radical center, it has delta minus charge that can push in and get that carbon closer to 8. And since we're starting at 7, we're closer to 8 than if we were starting at 6 if you had a carbocation. So now we've got our CH3 dot. And what does our CH3 radical do? It reacts with a bromine, an intact bromine molecule. Now, in the initiation step, you don't need all of these bromines to break apart. You don't need that. What you need is you don't need all the bromines here to break apart. You just need basically one, so that you can form a couple of radicals that'll then come down here and form the carbon radical, which will then form, that carbon radical will then form the product. So there is still a lot of intact bromine. And so what happens is the bromine breaks. Each bromine gets a dot, and one bromine pairs up its dot with the CH3 dot. So again, the arrows look like this. My transition state would have the CH3 partially bonded to the bromine, partially bonded to the other bromine. And then on the other side, I'm going to make my product, my methyl bromide, and I generate a new bromine atom. So those are the two propagation steps. The first one to make the alkyl radical, and the second one for the alkyl radical to react with an intact bromine to make the product, but it also generates another bromine atom. Okay. And this is the problem with free radical reactions. When you do a free radical reaction, when you make a radical, you generate another radical in the end. So every radical generates a new radical. And the process doesn't stop until you run out of stuff. Okay. So this is propagation. One radical propagates another radical. But this is where we get our product from. Okay. So these are the first 3 steps. And I said we had 6. So we still have 3 steps left. Okay. Everybody with me? I mean, we'll find out whether you can write this mechanism on your own, because I'm gonna make this a take-home homework problem for tomorrow. I'll give you one here at the end that you can do on your own. And will you have to do this next week? Yeah. Okay. So now, what are the next 3? The next 3 steps are called termination steps, because we have to stop the process. So how do we stop the process? We have to terminate it. And so how do we terminate it? Well, the way you terminate it is take 2 unpaired species, have them donate their electrons to each other, and form the molecule. So we have 2 unpaired species. The first thing we have is a Br dot, and the second thing we have is a CH3 dot. So the 3 reactions, the 3 termination steps, are going to be reacting a bromine atom with another bromine atom, reacting a methyl with a bromine, and then a new compound gets formed, because what if 2 of the alkyl radicals come together? Then that gives us a new product, which I'll talk about in a minute. So really, if you think I've got radical A and I've got radical B, the termination steps are 2 A's, an A and a B, and 2 B's reacting together. So the arrows, my 2 bromines are going to donate their unpaired electrons towards each other. What is my transition state going to look like? It's going to look surprisingly like the one I just wrote before, because transition states don't tell you whether you're making or breaking bonds. They just say there's a partial bond. And then we'd end up reforming bromine. So if 2 bromine radicals come close together, they can come together to make bromine. The methyl and the bromine can come together. The transition state there is going to have a dotted line between the methyl and the bromine. And it's possible I can make product in that termination step. The third step is a new product. And this reaction, whenever you bring 2 alkyl radicals together, that's called a coupling reaction. So these 2 radicals are going to couple together, same arrows. I'm going to have a carbon-carbon partial bond. And now I'm going to form a new product called ethane. And so the importance of that reaction is that if I proposed all of these steps, then that coupling reaction has to be one of them. So when I do a free radical reaction, in order for me to validate that this mechanism could be correct, I need to find some of that product. And if you were to analyze this primarily by something like gas chromatography, mass spectrometry, then you would find that ethane molecule, or you would find that coupling product present. It wouldn't be a lot, because remember, these radicals, as they're floating around in solution, they have to come close together to react. When you make a CH3 dot, it's most likely to find bromine, a Br2, and do a reaction. But these three termination steps are how we stop the process. Right. So those 6 steps are the way you write the mechanism. Now I have...
You said that's how you stop the process. Is that like controlled, or does that happen on its own?
It happens on its own. There's probably ways to control this, but for the most part, if I just take some pentane in a bottle and I add a couple drops of, well, I add some bromine to it, some orange bromine, and I put it over in the sun shining, the sunlight's enough to cause that reaction to occur, and over time what you would see is you would see the orange color dissipate as you're forming the product. And when I took the cap off of it, there would be a lot of smoke coming out, because that's the HBr, because there's no aqueous solvent in there to absorb it, so it would just, some HBr gas would come out. And when it hit the water vapor, that's what causes the smoke. So it's a very easy reaction to do, it's just not a very easy reaction to control. Because if I really did this reaction, I would have multiple bromines adding to multiple carbons. And all the reactions we're going to do, we're going to add one halogen to one carbon. But in reality, you would get di-bromo products, you'd get some tri-bromo products. If it was a pentane, you'd have all the combinations, 1, 2, 1, 3, 1, 4, 1, 5. And so you'd have a mess of products. So it has to be a little bit more controlled, but we don't control it. We'll establish some control, but we always talk about monobromination. We never talk about dibromination. But that's a real product. Okay. All right. So that's the mechanism. What's the rate determining step of this mechanism? What's the most important step? The most important step is going to be the one where we generate the radical, the alkyl radical. That's going to be the most important step. Now, the first half of chapter, 18. The first parts talk about bond dissociation energies and all of that. I'm not going to go into that. Bond dissociation energies, if I want, in this case, I'm forming an HBr bond and I'm breaking a CH bond. So if I wanted to know like what the delta H of that reaction would be, then I would say, well, it's going to take me so much energy to break the CH bond, and I'm going to get back so much energy by forming the HBr bond, and so it would tell me whether that step is endo or exothermic. That is going to be important. And we're going to find that that step is actually endothermic for bromine. If I changed it to chlorine, chlorine would be exothermic in that step, if you went through and did all the calculations. Okay. Because on the periodic table, bromine is less reactive than chlorine, which is less reactive than fluorine. And we're not going to do this with iodine because the reaction's too slow. And we're not going to do, well, if we do this with fluorine, it'll be a relatively straightforward reaction. But we would only do this on paper because fluorine's going to react explosively with alkanes. Because fluorine is one of the most reactive substances, on the periodic table. It's probably fluorine at the top and francium and cesium at the bottom in that diagonal. So fluorine gas, there's a problem with even putting fluorine gas in a container, because fluorine will destroy stainless steel. It'll react explosively with alkanes. And so in order to put fluorine in a container, they needed to invent Teflon. That's where Teflon comes from, the fact that people needed to put fluorine inside of a container. So they needed to coat the inside with Teflon. And just as an aside, Teflon has a long chain of carbon atoms with nothing but fluorines attached to it. Right? It is non-stick. Right? I don't think it's in vogue in cooking ware anymore, but it used to be. You used to have the Teflon in your cooking ware, but I think somebody said it was unhealthy, so it's not in there as much. But you still use it to make anything non-stick. They had to make this in order to put fluorine inside of steel containers to separate the uranium isotopes in the Manhattan Project when they were developing nuclear weapons. So the way that you separate out the different uranium isotopes is you convert the uranium into uranium hexafluoride gas, and then you use diffusion, like you learn about in general chemistry. You have basically pores, and you allow the gases to diffuse, and they'll diffuse based on their molecular weight. And then you can use these centrifuges to diffuse it, which is what all the controversy with Iran is, right? They turn up their centrifuges, they're enriching uranium ore to make nuclear weapons, right? So in the Manhattan Project, that all had to be developed. And so they needed a way to contain the fluorine gas, and so they had to develop Teflon in order to coat the inside of the steel tanks to keep the fluorine from basically destroying them. So we're not going to use fluorine, except on paper maybe, to do this free radical halogenation. That is uncontrollable. All right, so that's the aside. That's the practicality or the unpracticality of fluorine gas. Okay. Chlorine gas, we use that as a disinfectant. Right. You can use that as a disinfectant. You can bubble it into water at a pool to kill the bacteria. You can do that with water. They do that at the drinking water plant. If they do it at the drinking water plant, this free radical reaction can occur with organic materials in the drinking water. So they have to test it to make sure there's no halocarbons in your drinking water, because there's a certain threshold of parts per billion level that you have to keep below for the drinking water, because otherwise then you're drinking chlorinated materials, and those can be a little bit toxic. They're probably more carcinogenic than toxic. Okay. So this is the free radical halogenation steps. And this will occur with chlorine or bromine. And we'll talk about the differences here as we go along. Right. Okay, everybody with me? Next question. Let's make this more complicated. I'm going to substitute 1 hydrogen with 1 bromine. So my question now is going to be, if I do this reaction with pentane, how many different products can I form from substituting a hydrogen with a halogen? So how many structural isomers are possible for the reaction of pentane? How many possible products are there? I heard 5.
And then have fine with the other products like 1.
I'm only talking about monobromines.
Okay, then 5.
5. Other numbers?
Wait, we're just adding 1 bromine?
Just adding 1 bromine. We're replacing a hydrogen with a bromine. So how many? Let me ask it a little bit. 3? How many unique products are there? Unique meaning unique. Actually, unique meaning a product with a different name, because that's how you're going to know they're structural isomers. So if I replace any of the hydrogens on the CH3 here, if I replace any of those hydrogens, what am I going to get? I'm going to get 1 bromopentane. What if I replace one of the hydrogens over here on this methyl at the end? I'm going to get 1 bromopentane. So those 2 methyl groups are going to give the same product. Now, what about this? What about the CH2 here? Then I'm going to get Then I'm going to get 2 bromopentane. So that's a different product. How about replacing that, any of those 2? What am I going to get? We get 2 bromopentane. How about the CH2 in the middle? New product, 3 bromopentane. So I like to use letters to indicate which hydrogens are going to give me the same products. And then I can say, well, this is product. Okay, we're done with this mode. So then I could say, this is A, this is B, and this is C. For 5 of you, this looks pretty familiar, doesn't it? Because this is how we're telling the difference, which hydrogens give the different peaks in the NMR spectrum. And had we have gone over this, then I would have started that conversation by saying, how many unique products do we get in free radical halogenation? But the idea here is if we substitute a hydrogen with a bromine, if we think two hydrogens will give the same product, then replace them one at a time with bromine, name them. If they have the same name, they'll give the same product. And I will write them down with the same letter. Okay. So there are three possible products when I halogenate pentane. Bromine, chlorine, fluorine, it doesn't matter. Okay? Tell me, and then write what the, I want to know how many products, and then what I'd like you to do is to draw out the three possible, that number doesn't mean anything. Because that may or may not be the correct answer. 3 was the one from above. That was the correct answer. So write out the unique products for this reaction. You can write those out on your little board and then show them to me, and then we'll figure out how many we've got. So if you're unsure, replace the hydrogen with a chlorine, name it. Same name, same compound. You're okay. For the last one, you always want to make sure that you show, Cameron, you want to make sure you always show that I can clearly see the bond between the carbon and the halogen. Same thing. Now you want to when you write out your structure, make sure that the bond between the carbon and the chlorine is easily identified, so it doesn't look like the chlorine is just attached to the, for the upper right one, where's the chlorine? You need one more, and 2 of those are the same. Are any of those the same? Okay. Okay. I think well, I think you still need one more. There's still one more that's unique. Okay, are any of those this? Are there any that are the same? Okay.
I don't know.
See, you're missing methyl group. You're missing methyl groups. So when you do this, the first thing you do is this. draw the skeleton out, and now let's start replacing hydrogens with a chlorine. So, that one. I mean, it's the first product, so is it unique? Yes. If I labeled those CH3s A, are there any others that if I replace the hydrogens would be the equivalent structure, would give the same product? What about these? So in other words, is this product and this product the same? Yeah. If I was to name them, I would name this 1-chloro, 2-methyl butane. This would be 1-chloro, 2-methyl butane. So those two are the same. So these two products are the same. And so that means the A would go on both of the methyl groups. Now, here's a real easy way to at least get the unique ones right off the bat. A CH3 is never going to give the same product as a CH2, which is never going to give the same product as a CH. So if you've got a CH3, CH2, and a CH, they're all going to give different products. The question is, if you have 2 CH3s or if you have 3 CH3s, are they going to give the same product? So I can very easily whip through these and say CH3, CH, CH2. And so this would be product A. This would be product B. And this would be product C. And again, notice I'm starting with the same skeleton. And one of the things that, you know, after grading thousands of these problems, and it literally is thousands after 100 a year for 25 years. That's more than 1,000. The thing that people will make mistakes on is you've got to show this bond. You've got to show that bond, because people will just put the chlorine at the end. General rule for me grading, my psychic powers end when I grade, so that whenever I try and guess, you know, if you put a chlorine there and I say, well, I guess maybe the chlorine, they meant that chlorine to go at the end of that bond, I always guess wrong. So if you write me an answer where I have to guess to give you the correct answer, I always guess wrong. So that means don't make me guess. Okay? So that's something you got to make sure that you clearly put the bond in. And then the real question is, so what about this CH3 over here? Is that CH going to give the same product as A? No. It's not, because if I write that structure out, now with my chlorine like that, naming it would be 1-chloro, 3-methyl butane. And that's a new name. So this one's going to be D. So that's going to be product D. So CH3, CH2, CHs will always give unique products. If you've got 2 CH2s, you have to make sure, are those the same or not? And for these two methyl groups, if you go back all the way to naming, remember if we had a long chain and if I went this way, I would get the same name as if I went the other way. So if I go up, if I take my long chain and I go up here, or if I take my long chain and I go that way, If I get the same name, then that means those two groups. The fork in the road really isn't a fork. Either way, those two are going to be equal to each other. Okay. So in this case, I've got four unique products. We'll do one more. And I will still do more, but okay, write them. I mean, a number's okay, but I want to see the unique products. Okay. 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 Now let's see. Okay. Yep. Need some more. Those are unique. Those are unique. Now you need a few more. Okay. Right. Okay. Yep. Okay. And so you're going to want to make sure that you put your letters in as well. Yep. So we've got an A, we've got a B, we've got a C. The CH3, CH2, CH in the ring. That's going to be different. Is there a group that's the same? It's going to be this one down here. Is that one different? Yes. The one across. So in other words, what I'm doing here, you can also use mirror planes for this. So if you think about, I rewrite the molecule like that, there's a mirror plane that's going to make D, the D's the same, and the E's the same, and then F is going to be unique. Okay, so we can use a combination of naming, mirror planes, whatever is necessary, so that we can be able to label the products. So there are 6 different products for this. So a BR there, a BR there, a BR there, a BR there, 1 there, and 1 there. So there are my 6 products: A, B, C, D, E, and F. So at this point, for free radical halogenation, the most important part of the mechanism is the formation of the free radical, of the alkyl free radical, and that's going to come into play in the next part. If I do a free radical reaction on a complicated molecule, I now have to be able to write all the possible products. And the next step is, what's the major product of this reaction? And in order to understand what the major product is, I need to, well, I'm going to ask you what you think. Let's do this one. Let's take propane. Let's add Br2 to it. How many possible products are there going to be? Two. So there's going to be 1 bromopropane, which we'll call product A because A would come from the 2 CH3s. And then there would be 2 propane from the CH2, which we'll call B. So we got 2 products. Normally I would say, well, when we have 2 products, what's the next question? The next question is, what's the major product? You tell me. And I guess if you read ahead, you'd be able to tell me that. But if you didn't read ahead, or if it didn't make any sense, tell me what I should be looking for. You can make a case for either one of these 2. Megan? Secondary. Okay, so one way to look at this is to say, which of these 2 products came from the most stable radical intermediate? And that would be product... That would be product B. That would be product B. Right? Because B came from a secondary radical made B. So you could make an argument to say, well, B is going to be the major product because it came from the most stable intermediate. Have we done reactions like that in the past? Absolutely. Right? Why is Markovnikov's rule the way it is? You add the electrophile to the carbon to give the most stable carbocation. That is where the major product came from. We've also done, and I'm going to just caution, because we've also done reactions where we formed the most stable product. But here's the issue here. I don't have rules about halogens. There are no rules about what's more stable, a primary or a secondary halogen. So the next approach would be to say, okay, then maybe the most stable product is. But the product, we have no way of determining which one's more stable. So we can't use that approach. But could somebody make a case for A being the most stable product? Just thinking about the process. Okay, I like that. So if you're a BR dot and you're just randomly going around deprotonating or abstracting hydrogens, there's 6 A hydrogens and there's only 2 B hydrogens. So just statistically, which hydrogen are you likely to come into contact with? With the A's. Now you could also make the case that since they're CH3s, they're going to be less sterically hindered, although that argument works in this case. But from a pure statistical standpoint, if you're a BR dot, you could make product A 6 different ways, and you can make product B 2 different ways. So you can make the case that A is going to be basically what we would call a statistical product. So if the stability of the radical doesn't play a role based purely on statistics, A should be the major product. Does that argument make sense? So I've got 2 arguments here for forming A and B. And the statistical argument will always go against the stability of the radical. Because the more hydrogens you have attached to the carbon, the less stable the radical is going to be. So these 2 arguments are opposing each other. So what is the major product of this reaction? Is it A or B? Well, my answer is going to be, it depends. And then your question should probably be, on what? Right, what's it going to depend on? Well, here's what it's going to depend on. Am I doing bromine or am I using chlorine? Am I doing the reaction at room temperature or am I doing the reaction greater than 300 degrees Celsius? So I do the reaction at room temperature or high temperature, which really is room temperature and light versus greater than 300 degrees, which is pure heat. It's going to depend on those 2 things. And so we have to talk about that. Why does it depend? Now, when this is a first semester topic, which it very well may be when I teach this in the fall, because it screws everything up otherwise. This would be our entree into topics like the Arrhenius equation, Hammonds Postulate, activation energy, So we're going to need those topics in order to make these explanations. And when I go back through, I'll refresh on what each one of those is, if you haven't heard about them in a while or ever. Okay. Now, what do we want to do first? Let's do bromine versus chlorine. What was the most important step in the mechanism? The most important step in the mechanism is when your halogen atom reacts with your alkane, forms your HBr, your HCl, and forms the radical. Now, let's talk about the role of the stability of the radical in this reaction. But in order to do that, I'm also going to have to talk about the difference between chlorine and bromine. So when this reaction is chlorine, this step is exothermic. Whereas when this step is bromine, the overall this step is endothermic, which basically means that when I'm using chlorine, my step is going to look like this. And when I do bromine, my step is going to look like this. And how do I know that? Because this is my reactant, this is my product, and that's really not the case, right? The product's going to be the intermediate radical. But when I look at this step, it's either exo or endothermic. Remember, energy goes up in each one of these cases, so this is exothermic because the reactant is giving up energy to form the product, so it's releasing energy. This one over here is endothermic because the reactant is getting energy to go to the product. And in this case, the product is the radical intermediate. So which one of these two reactions should occur faster? Chlorination or bromination? Which one should be faster? Cl? Why? Because it has a smaller activation energy. Why does an exothermic reaction have a smaller activation than an endothermic reaction? And that's because of basically the Hammonds Postulate. So if you remember with Hammonds Postulate, if we take a piece of paper and we have a reaction that is thermoneutral 50-50, the transition state's right in the dead center of the reaction coordinate diagram. As I make the reaction endothermic, as I raise the product energy, then what happens to the transition state? It moves towards the products. And that's what Hammonds Postulate said. Hammonds Postulate said in an endothermic reaction, the transition state should look more like the products. In an exothermic reaction, then, the reactants look more like the transition state looks more like the reactants. He didn't really say anything about transition state energy, but that's what follows. And he never intended it to be used as sophomore level organic or beginning organic. But we've interpreted it along the way, and we've included it probably in the last 10 years to be able to explain this. So where does that come into play? Where would Hammonds Postulate come into play? Well, let's imagine that I have a choice for the chlorination between forming a primary radical and forming a secondary radical. Which one's going to form faster? And this is not, this I just wrote is not to scale. It's pretty crappy. But as I pull down the energy of the intermediate, what happens to the activation energy? The reaction becomes more exothermic, and so you're going to have a lower activation energy here to form a secondary than you will a primary. How do we translate this activation energy to rate of reaction? Remember, we have rate equals A e to the minus EART. This is the Arrhenius equation. And in the Arrhenius equation, the lower the activation energy, the faster the rate. The higher the temperature of the reaction rate increases. The bigger the activation energy, the slower, and the lower the temperature, the slower. It's the Arrhenius equation that gives us all of that mathematically. We don't really use it mathematically, but if we did, that's the translation between stability of the intermediate and reaction rate through Hammonds postulate, through the Arrhenius equation. Now, notice that this is an exponential function, right? So if I double the temperature, I don't double the rate. Like usually it's what? For every 10 degrees Celsius rise in temperature, you double the rate of the reaction. Is my recollection. Give me 5 degrees either way, and I know I'm right. So as we go up in temperature, we increase the reaction rate, but it's not linear, it's logarithmic. Now, this is going to occur, this diagram is going to occur for both of these reactions. So it's always going to be, each one of these two reactions is always going to form a secondary radical faster than a primary radical. Okay. It's always going to form a secondary radical faster than a primary radical. But one is endo and one is exo, and that is going to play a huge role. So what we really need to do is this. We need to figure out how fast radicals are formed in each one of these two cases. And I can't determine an absolute rate, but I could relate everything back to a primary radical. Okay. So I'm going to go off on a little, not a tangent, well, it's a tangent. I'm going to go off on a little bit of a tangent here. We need numbers. Because right now I'm just saying, oh, in both cases you form a secondary faster than a primary, and you're going to form a tertiary even faster. But I need numbers to go with that. So how am I going to get those numbers? Well, I can write them down, but where do they come from? They come from basically taking, let's say I take this molecule. I take that butane, 2-methyl propane. I take the 2-methyl propane and I do a halogenation on it. And I know I'm going to get two products. I'm going to have my product that came from the primary radical, and I'm going to have the product that comes from the tertiary radical. So I go to the lab, I do my halogenation, I get my mixture of products, I shoot it into a GC, and I get the percentages. Okay. And I'm not going to make up numbers on percentages other than to say percentage primary, and percentage tertiary. So I get those percentages from the GC. Now, does that tell me how quickly I produce my radical? No, because I have a complicating issue. My complicating issue is how many different hydrogens give me the primary product? 9. Right? I've got 3 CH3 groups. So I've got 9 hydrogens that'll give me that product, whereas tertiary product, how many hydrogens do I have? Just 1. So what I have to do is I have to divide that percentage by 9 hydrogens and divide this percentage by 1 hydrogen. Because I've got to do what's called normalizing for the number of hydrogens. I've got to take the statistics out of this equation. And so that's the way I do it. I'll say, I'm going to get my percentage, I'm going to divide through by the number of hydrogens to get me that product, and I'm going to take the ratio of these two products, or the ratio of these two numbers. So in other words, I'm going to say, I've got tertiary, not percentage tertiary, but I'm going to divide those through, and when I do that, I'm going to have a number for tertiary to primary. That is going to be the relative rate of forming a tertiary product over forming a primary product. The relative rate of forming a tertiary radical over a primary radical. Right? So I'm just going to take and normalize for hydrogens. And then I'm going to take a whole bunch of other molecules and I'm going to do the same thing. So in the end, I'm going to have a relative rate of forming the carbocation by removing all the statistics. Sorry, not a carbocation, a radical. I'm going to have the relative rates of forming radicals independent of statistics, but they're all going to be relative. So it's going to be tertiary to secondary to primary, and primary is always going to be 1. So fortunately, we don't have to do that. People have already done this, and they don't vary that much. The numbers that I've had in my head for the last 20 plus years, I'm going to use. If they're slightly different than the book, they're slightly different than the book. So here's what we find. For chlorination, you form a tertiary radical 5 times, there's a decimal point here. No, there isn't. 5 to 3.4 to 1. So you form a tertiary radical 5 times faster than a primary radical. And in secondary, you form a secondary radical 3.4 times faster than a primary radical. And if you wanted to go tertiary to secondary, it would be 5 over 3.4. So this is independent of statistics. This is now how much faster we form a radical when we do chlorination. That's perfectly legitimate with what I said before and with the Hammonds postulate, right? We should form a tertiary radical faster. We should form a secondary radical faster. Now we have numbers. And here's the problem. The problem is those are the numbers for chlorination. I'm forming the same radical whether I do chlorination or bromination, right? So why am I going to write down a different set of numbers for bromination than chlorination if I'm forming the same radical? Well, I'm going to. So what we find is that you can form a bromine or a radical in bromination, tertiary one, 1,700 times faster than a primary, and you form a secondary 80 times faster than a primary. So these relative rates of forming the carbocations, the radicals, the relative rates of forming the radicals are what we call the selectivities. And the problem is, they're different. If I could do fluorination, they would be 1 to 1 to 1. I would form the radicals at the same rate. And if I go greater than 300 degrees Celsius, regardless of whether it's chlorination or bromination, greater than 300 degrees, they're 1 to 1 to 1. So I form all the carbocations at the same rate. But I'm forming the same radicals. So why am I forming them at a different rate? And the reason for this is, and again, it's not statistics. Statistics are wiped out of this equation. It's because chlorination is exothermic, bromination is endothermic, and fluorination would be super exothermic. And then we still have the heat left over to deal with. So, why are the numbers different? And we'll do this sort of non-mathematically, but everything boils down to the Arrhenius equation. So let's take chlorination first. And before we do that, what does selectivity mean? So bromine is more selective in forming a tertiary versus a secondary versus a primary. Right? Those rates are much different. So it's more selective at forming tertiary. Tertiaries are formed preferentially faster. When you get to chlorine, it's only 5 to 1 as opposed to 1700 to 1. So we would say bromine's more selective in forming a tertiary than chlorine is. And why is that? I'm going to try and draw a better diagram here. So here are our two diagrams forming a primary and a secondary for chlorination, and here is the diagram for forming primary and secondary for bromination. And here is the key. And there is the equation that tells us all about the math. So we could do this totally mathematically and try and figure out what the transition state energy difference is, and then apply a temperature to that. And so this equation is telling us the rate of forming the radicals. And we would need to know the transition state energy difference between primary and secondary for each of these cases. And mathematically that will work. But let's talk about birds and hikers and mountains. So, what gives the molecules the ability to go over the activation energy barrier and form the product? It's thermal energy. It's the energy that's available to the molecules at a particular temperature. And if you change the temperature, you change the average kinetic energy of the molecules. So what's happening is collisions. When two molecules collide, One gives the other the energy to go over the activation energy. So it's temperature. So at room temperature, you have a certain amount of energy. So which barrier are you going to overcome fastest? If you're the hiker, you're going to overcome the small mountain. You're going to go over the small mountain. In chlorination, it's going to take you longer and more energy to go over the big mountain for bromine. And it's going to take you more energy to go over the primary mountain versus the secondary mountain in each case. If your bird's flying over the mountain, then again, it takes a certain energy to get over the top of the mountain. Where's that energy coming from? In molecules cases, it's coming from temperature. Now let's deal with the increase in temperature situation first. So I want to make the birds fly over the mountain faster. What do I give them? I can't change the size of the mountain. All I can do is give the birds more. I want the hikers to go over the mountain faster. All I can give the hikers is more energy. I want the molecules to go over the activation energy faster. I give them more energy in the form of raising the temperature. Okay? Now, if I do that, the molecules are going to go over each barrier faster. And the relative rates of overcoming both of those barriers is going to get smaller. So as I raise the temperature, there's going to be a point where the molecules can go over either barrier equally well. Or better yet, equally fast. It won't be exactly the same, but it'll be pretty close. So when you get to about 300 degrees Celsius, the mathematics of the Arrhenius equations say that the relative rate of primary versus secondary are going to be nearly the same. And if you go to 300 degrees Celsius, the rate of the bromination, the rate of overcoming both of those barriers, is going to be nearly the same. So at 300 degrees Celsius, that's like having supersonic birds. They go over any mountain at the same rate, no matter how high it is. Small mountains, same rate as high mountains. Okay? It's a stupid example, but it works. We can't have supersonic hikers unless they're being carried by the supersonic birds. Then we should probably go Game of Thrones dragons, right? Supersonic dragons. Dragging hikers over the mountain. But that's the significance of 300 degrees Celsius. Now the molecules overcome any barrier at nearly the same rate, and we basically say they overcome it at the same rate. So you form a primary, secondary, or tertiary radical at the same rate at 300 degrees Celsius. Okay? So that's the easy explanation. Why do you form a secondary radical 80 times faster than a primary, but down here you only form it 3.11 times faster with chlorination? Well, what the 3.4 to 1 means is that the relative rates of forming a secondary radical the relative rate is smaller. So in other words, you form a secondary radical in chlorination pretty fast. Not as fast as a primary, or a little bit faster than a primary, a little bit faster, 3.4. Whereas when it's a secondary, it forms at a lot slower than the chlorination. And the reason for that is because the relative differences between the activation energies when the reaction is exothermic, the relative energy levels is a little bit smaller than if you're trying to do this with an endothermic reaction. So in other words, these differences in the activation energies are much larger when the reaction is endothermic versus over here, those activation energy differences are smaller when it's exothermic. Now what's playing the role there? Temperature. So in other words, molecules to go over the two barriers at room temperature where they have lots of energy are going to be able to go overcome both barriers at somewhat the same rate. If you want to consider 3.4, that's not that much different than 1, whereas 80 is hugely different. So there's not enough energy at room temperature to make the bromine go over the two barriers at nearly the same rate. So those molecules are starved in bromination. They've got a bigger barrier to overcome with the same amount of energy. In chlorination, they have enough energy to overcome both barriers at a relatively fast rate. So it's the difference between exo and endothermic. Now how would you make chlorination go from 1 to 3.4 to 1 to maybe 50 to 1? I got really healthy birds with a lot of energy, and they can overcome the two barriers at nearly the same rate. How do I differentiate the rate? Take away some? Or what? Yeah. Make the birds less energetic, starve the hikers. The less energy they have, the bigger the differential is going to be in going over those two peaks. So if you want to make chlorination more selective, lower the temperature. If you want to make bromination more selective, lower the temperature. So the reason that bromination is more selective is because it's endothermic and the differences in the activation energies is larger. And at 25 degrees Celsius, it's enough to make those barriers pretty significant. So tertiary, 1,700 times faster. Secondary, only 80 times faster. But compared to chlorination, where you've got small barriers, and that 25 degrees is a lot of energy to do that, it's going to go over the barriers at faster relative rates. So now it's only 5 times faster to form a chlorine, or to form a tertiary. It's only 3.4 to form a secondary. So the reason for the difference in selectivity is not the stability of the radical, it's the same radical. But what's different is the energy diagram's different, because in one case it's a small activation energy because it's exothermic, it's a large activation energy because it's endothermic. So, final thing, and then we'll take a quick break. And then we'll come back and figure out what the major and minor products are, now that we have these tools that we don't know how to use yet. Okay. I said originally that the percentage of the product was equal, or sorry, I created this thing called selectivity by taking the percentage of the product and dividing through by the number of hydrogens. That's how I created selectivity. Now what I want to do is I want to calculate percent product. So that means that now my equation is going to say the percentage of the product is going to equal the selectivity times the number of hydrogens. And so now if I want to calculate the relative amounts of the products, I can use this equation, and all I need to do is be able to count the number of hydrogens that give me each product, and then know my selectivities, which I will always give you. Then you'll be able to calculate what's going to be the major product of the reaction. Whether it's bromination, whether it's chlorination, or whether it's greater than 300 degrees Celsius. So that's a lot. The explanation, of why selectivities are different. That's usually where we introduce the idea of Hammonds postulate and the Arrhenius equation and all of that. All right. So let's take a 5-minute break or so. So we'll start back at 20 till. At the end of class, right? Haven't I been giving